Baseload power plants are required to run constantly for long periods of time in order to provide energy for the regions of continuous demand. Therefore, using vapor as the working fluid is economically reasonable. The Rankine cycle consists of four main processes. The first one is an isentropic compression in a pump. The second one is a constant pressure heat addition in a boiler. The third one is an isentropic expansion in a turbine. And the fourth one is a constant pressure heat rejection in a condenser. This is known as the ideal Rankine cycle. The temperature entropy diagram is the following. The green lines represent the pressure, which is constant. The blue lines represent isotropic processes. The formulas used are the following. As you can see, all formulas have H's. This is a property called enthalpy, and you can find the value in any table of saturated water or superheated water. Another properties that you can find in these tables are a specific volume, internal energy, and entropy. The efficiency formula is the following. Now let's work a problem. A steam power plant operates on the simple ideal Rankine cycle. The boiler operates at the pressure of 6 megapascals and the condenser at 50 kilopascals. At the entrance of the turbine, the temperature is 600 Celsius. The fluid enters the condenser as saturated vapor and the pump as saturated liquid at the condenser pressure. The pump and turbine work are isotropic. Find the efficiency of the cycle. The given information is the following. At the condenser, the pressure is 50 kilopascals and is saturated vapor. At the boiler, the pressure is 6 megapascals. At the turbine, the temperature is 600 Celsius, and at the pump, the fluid is saturated liquid. This information is enough to draw our diagram. Let's start with the condenser. We know that the pressure is 50 kilopascals and is saturated vapor. The boiler pressure is 6 megapascals. The fluid enters the pump as saturated liquid, and the pump and turbine work are isentropic. As it can be seen, the pressure in the pump is the same as the condenser, and the pressure in the turbine entrance is the same as the boiler. Using the table of saturated water, the values of a specific volume, entropy, and enthalpy are the following. Now, let's find the work done in the pump using the following formula. Using the specific volume and pressure 1 and pressure 2, the work done in the pump is 6.13 kilojoules per kilogram. The enthalpy in stage 2 is the following. 346.67 kilojoules per kilogram. For the turbine, using the superheated water table, the enthalpy is the following. For the condenser, using the saturated water table, the enthalpy value is the following. Now that we have all the enthalpy values, we can calculate the heat in and heat out to calculate the efficiency. The heat in is 3,312.13 kilojoules per kilogram. The heat out is 2,304.66 kilojoules per kilogram. And the efficiency is 30.4%. The actual steam power efficiency is lower than this value due to all the frictions present in the system. Currently, the Lunen hard coal-fired power plant in Germany has an efficiency of almost 46%. It produces 750 megawatts of electricity and can provide electricity for around 1.5 million households. It is the cleanest and most efficient hard coal-fired power plant in Europe. Brayton cycle is known to be the ideal cycle for gas turbine engines. They are generally used in all peaking power plants. Plants like these are able to have a quick start and reach their working temperature in a considerably faster rate than the baseload plants. This is convenient as they are constantly run for long periods of time, but only when higher power requirements are expected. The Brayton cycle is made of four internally reversible processes: isentropic compression, constant pressure heat addition, isentropic expansion, constant pressure heat rejection. The thermodynamic cycles used for small power generation applications are the Otto and the diesel cycles. These are most commonly found in motorized vehicles. The Otto cycles require spark ignitions, whereas the diesel cycles uses compressive ignition. In today's industry, the Otto cycle is generally used on applications that require smaller amounts of generated power. The automotive industry is the biggest example of the application of the Otto cycle and diesel cycle. And for every car running on a spark ignition engine, the Otto cycle is used as it is known to be the ideal cycle for these types of engines. The ideal Otto cycle is made of four internally reversible processes. The first one is the isentropic compression. The second one is the constant volume heat addition. The third one is the isentropic expansion. And the fourth one is the constant volume heat rejection. The temperature entropy diagram is the following. The pressure specific volume is the following. The formulas used are the following: for heat addition, for heat rejection, for compression ratio, for the relation between pressure and a specific volume, and for temperature and a specific volume. K is the specific heat ratio of air, which is equivalent to 1.4. With these formulas, we will be able to calculate the efficiency of the Otto cycle. Now let's work a problem. An ideal Otto cycle has a compression ratio of 7. At the beginning of the compression process, air is at 35 Celsius and 0.1 megapascals. The maximum temperature of the cycle is 1100 Celsius. Find the cycle efficiency. The given information is the following. For compression, the temperature is 35 Celsius and the pressure is 0.1 megapascals. The compression ratio is 7. The maximum temperature is 1100 Celsius. This information is enough to draw the temperature entropy diagram, which is the following, and the pressure specific volume diagram, which is the following. Using the compression ratio, we can find the temperature in stage 2. Remember to use the temperature in terms of Kelvin. Temperature 2 is equal to 670.8 Celsius. The pressure in stage 2 is the following: 1524 kilopascals. For process 2-3, the pressure 3 is given by the following formula, which is equivalent to 3119.34 kilopascals. For the temperature 4, which is isentropic, the value is 630.39 Kelvin. With this information, we can find the heat input and the heat output to calculate the efficiency. Cv is the specific heat value of the air, which is 0.718. The heat input is 504.18 kilojoules per kilogram, and the heat output is 231.44 kilojoules per kilograms. There are two ways that we can calculate the efficiency. The first one is to use the heat input and the heat output, which is equal to 0.54. And the second one is by using the compression ratio and the K value, which is equals to 0.54. In both cases, we got the same value. The diesel cycle is similar to the Otto cycle, which is the one used in gasoline engines. The main difference is that the spark plug and carburetor in the gasoline engines is replaced by the fuel injector in diesel engines. The diagrams of the temperature, entropy, and pressure and specific volume of the diesel cycle are the following. Thank you very much for watching. If you like this video, give it a thumbs up and subscribe.